And today we're going to talk about this work and center of mass. And I'm going to switch to the shared screen. Okay, where am I? All right, and I'm going to bring up the set of notes. It says section 6.5. Okay, but since this was a different textbook, again, the chapter numberings may be off. But in this section, I believe it's 2.5. We're going to look at 2.4 or 2.5. We're going to look at work. And in everyday life, work basically requires muscular or mental effort. But mathematically, the way that we calculate work is by taking a force and moving that force said distance. Once we multiply those two, that would give us work, okay, in its most basic definition. Now, just another thing I want to point out about work itself. Work in SI units, its unit is a Newton meter. So whenever you are working with work, okay, that unit in SI, the SI system is Newton meter, which has a special name called the joule. In the British system, the unit of work is foot pound. Now, specifically for our class, you're going to see this word joule. And just keep in mind that when you're working with joule, that unit is a Newton meter, and that distance of measurement should be in meter. So if you're given something like, let's say, centimeter, you would have to convert centimeter to meter, right, when you're using work, specifically because of the unit that it's in. All right, so work, we sort of talked about the units. That's equal to the integral from a to b of f of x dx, right, where f of x is the force. Okay. Now we'll take a look at a couple of examples, but before we begin the examples, when we talk about force, right, force is directed along the x-axis from a to b. So notice we have our limits of integration are from a to b. When we're dealing with springs and when we're dealing with work, we must use Hooke's law to find the force. If we're not dealing with springs, we can simply take whatever function we're given, we can integrate it on the interval from a to b. Okay, so here's what I mean by that. If I go to the homework problems, okay, in 2.4, you just notice that there are only 4 problems in this section, and the videos are pretty good for this section. The only thing is, for question number 1, there is no video associated with it. Okay, but we're given this question. It says the force on a particle is described by 7x cubed minus 3 at a point x along the x-axis. We're asked to find the work done by moving the particle from its origin, right, which would be 0, to x equal to 5. Right, so I'm going to go back to the camera. All right, and we're going to work that out. Okay, so I'm gonna just write down what we have here. So we have a force on a particle is described by 7x cubed minus 3. Okay, so work would equal to the integral from a to b for f of x dx. Right, so we're actually given the force equation f of x, which is 7x cubed minus 3. Right, so keep in mind every integration must have a variable of integration. Every integral must have a variable of integration. Now for our limits. The limits are from a to b. So our limits for our particle movement are from its origin, which is 0 to 5. Right? So this is simply what we will integrate. All right. Now, as far as the integration is concerned, okay, I'm going to slight that a little by using the calculator. All right, so I'm going to use the integration function. So I'm going to hit math. I want to scroll down to function integration. I must put in my function, which is 7x to the third power minus 3, comma, every integral must have a variable of integration. Our variable of integration is x. Our limits of integration are from 0 to 5. So we have 1078.75. All right, so the very first one, even though there wasn't a video, it's sort of straightforward. We're given a force, we're actually given the force function. Okay, we're given the limits, and we simply put that in our work formula and integrate. All right, now problem number 2 is slightly different. Okay, we're given a force of 1 pound. So notice I am given a force, but I'm also talking about a spring. Okay, so before we go any further, we're going to look at what's called Hooke's law. And this is where the videos are pretty good in this particular section. So I'm going to bring up this video. And in the video, he describes Hooke's law. So we'll just take a look at that. Hopefully you can hear the video on this.
Where Hooke's law is a principle of physics that states that the force F, needed to stretch or compress a spring by some distance s, is proportional to that distance, and therefore F is equal to K times S, where F is the force, K is the spring constant, and S is the distance the spring is stretched. So
all right, so in Hooke's law, we have that F, which is the force, and we were given the force on our problem, that's equal to K. K is the spring constant, which is the unknown, which is what we must find, times S, which is our distance. So we're basically taking this F, which is K times S, and we're replacing that with this F of X. Okay, so keep in mind there will be a variable transform. Our Hooke's law gives us S as the variable for distance. We're simply going to convert the S to an X. All right. So if we go back to our problem, excuse me, we have that a force of 1 pound is required to stretch it to stretch a spring 4/10 of a foot beyond its natural length, how much work in foot-pounds is done by stretching the spring from its natural length to 1 foot beyond its natural length? And we're also asked to round exactly to 2 decimal places. All right, so I'm going to go back to the camera. All right, so this is example number 2. So work is equal to the integral from a to b for f of x dx. Since we're dealing with a spring, the first thing we must do is find the force constant. All right, so notice in the first problem, we did not have to find a force constant because we were not dealing with springs. Okay, springs are a special situation in which you must use Hooke's law. So here's Hooke's law. The force is equal to K, which is the spring constant, times S, which is the distance. If we go back to our problem, we see that a force of 1 pound, so in our formula, we're going to substitute F for 1, is required to hold a spring stretched 4/10 of a foot beyond its natural length. So our distance is 0.4. So S is equal to 0.4. Okay, I see there was a question. I'm going to switch back to the camera. Okay, I had connection issues as well. All right, but this is being recorded. All right, so you'll be able to go back and watch from the beginning. All right, so we're finding that force constant K. So we're going to substitute F for 1. We're going to substitute S for 0.4. So if I divide both sides by 0.4, I have 1 divided by 0.4 is equal to K. So basically, I'm going to remove the decimal. So if I move the decimal 1 place in the denominator, I have to move the decimal 1 place in the numerator. And then I'll reduce. 10 over 4 reduces to 5 halves. So 5 halves is equal to K. Right. So since we were dealing with the spring, right, we didn't just substitute F for 1 or whatever. We had to find the force constant K. So we substituted the force, which is 1. We substituted in the distance, which was 4/10. We solve for K. We have 5 halves K. So now we're just going to substitute into the work formula. Substitute into the work formula. So work is equal to the integral for 5 halves x dx. All right, so this is our force equation. So what are our limits? Well, if we take a look back at our problem, we're stretching the spring from its natural length to 1 foot beyond its natural length. So our limits of integration are from 0 to 1. Okay, now keep in mind I don't have to convert any units because everything is in feet. All right, so foot pounds. All right, they kind of give us our units, so there's no need to convert. All right, so here is our work integral. It's equal to the integral from 0 to 1 for 5/2 x dx. All right, so I'm going to perform this calculation on the calculator. All right, so I'm going to go into math, function integration. We're going to put in that function 5/2 x. X is the variable of integration. We're integrating from 0 to 1. And we have a value of 1.25. Okay. All right, now the third and fourth examples, the videos are real good at explaining, okay, these two, but I'll just kind of touch on this one a second because it works with this joule concept. So one thing about this particular problem, you're still dealing with a spring, right? So you're going to use the Hooke's law of force constant, okay? But in this instance, we're not actually given the force, we're given the work. So in this particular case, we can set our work equal to 1, right? We have our limits of integration. Okay, and as you'll see in the video, notice that this is in centimeters, right? And keep in mind from the unit of measurement, a joule is measured in Newton meters. So that centimeter must be converted to meters. Okay, and you'll kind of see that in this first video example. Okay, and also problem number 4. Okay, it's pretty much the same. The video on this is pretty good. All right. In this particular problem, we're finding the work done to pump all of the water out of a pool or over the side of a pool. All right, so I'll kind of refer these couple of problems to the videos. Okay, they do a real good job of explaining. Okay, in the very next section, and I'm sort of looking at this as in an instructor view, so my view is a little bit different from your view. We talk about moments and centers of mass. And I must warn you that in this section, the problems are twofold. And what I mean by twofold, there are two sets of formulas that are actually going on for these particular problems. Now, number 1 is a special case because in problem number 1, I'm not actually given a function. I'm just sort of given some masses. I'm given the coordinates for those masses, and I'm asked to find the center of mass for the system. If I just kind of visually look at problem number 2, problem number 2 is it's a little bit different. Here I'm trying to find a centroid. Okay, for problem number 3, notice that I am given an equation. For problem number 4, I'm given an equation. For problem 5 and problem 6, we're given equations. All right, so the way that we attempt to answer the first problem is different from problems 2 through 6. Okay, there's a completely different set of formulas. So what I want to do here in this section is we'll go through the very first problem. And then on next week, we'll go through the other set of problems, okay, because these things are really long-winded. We'll go through the second set of problems in the center of mass section, followed by the very last section in chapter 2, which is hyperbolic functions, after which we will have the midterm. Okay, so I'll kind of give more information on that midterm toward the end of class. All right, so let's take a look at this particular problem. Right, we're given 3 masses, right? Mass is the same as weight. So we're given mass 1 is 4, and we're not given any units. Okay, we don't quite know if this is pounds or kilograms, but we're given the mass of object 1 is 4, the mass of object 2 is 8, and the mass of object 3 is 6. We're also given the coordinates, right? So this is actually on an X and Y coordinate system. The mass of object 1 is located at the coordinates -9, -5. The object of mass 2 is located on these coordinates, and the object of mass 3 is located on these coordinates. And what we're asked to find is the center of mass for this system. Okay. Now I'm going to open up our textbook. So again, in order to open up the textbook, in the XYZ homework, right, there's a link that says ebook. Right, if you click on that ebook, it will bring up the textbook. Okay, on page 160, I'm going to go up. Okay, it talks about moments and the center of mass. All right, so just to introduce this, so just notice here, we basically have a seesaw or teeter-totter. And this triangle represents the fulcrum or the axis. Next, we have 2 objects. Okay, this first object is called M1, and it has a mass which is unknown at this point. It also has a distance from the fulcrum. We have an object of mass 2, and it also has a distance from the fulcrum. Okay, we don't know what these distances are, and we don't know what the masses are. But if we were to place these things on a rod or on a teeter-totter, in order for them to balance, we could balance them by moving our weights on either side of our fulcrum. When you talk about a moment is just a measure of the tendency of an object to rotate around a fulcrum or a point. I'm going to find the formulas that we're using. Okay, and here are the formulas here. In order to find the center of mass object in a plane region, we have this x bar, which is the moment on y divided by the mass of the system. Okay, and I'll kind of explain these in a second. And we have y bar. All right, these two coordinates would give us the location for the center of mass for our system. We have the moment on x divided by m, and keep in mind that m is the mass of the system. Okay. All right, so here's how we will proceed. Okay, let me stop my phone from. All right, so I'm going to go back to our problem. Okay, and I'm just going to write some things down. Okay, so let me actually see where I am in my broadcasting. Okay, so here is the camera. So we're given that m sub 1 is 7, m sub 2 is 8, and m sub 3 is 3. P sub 1 is -1, 4. P sub 2 is -9, 1. P sub 3 is 8, -4. And we want to find the center of mass. All right, so here are the formulas. So x bar, y bar, that's equal to the moment about y divided by the mass, comma, the moment about x divided by the mass. So here's our formula. All right, so what are these quantities? Well, m, that's the first thing we want to find, m, which is the mass of the system. So here's the formula. M is equal to m sub 1 plus m sub 2 plus ... all the way to m sub n. Right? So here I only have m sub 1, m sub 2, and m sub 3. So I'm going to add those together. 7 plus 8 plus 3. So m is equal to 18. All right? So that would be our value for m. Okay, so I'm going to put that to the side. The next thing we're going to do is we're going to find the moment about x. Okay, which is m sub x. So here's the formula. M sub x is equal to m sub 1 times y sub 1 plus m sub 2 times y sub 2 plus dot 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 m sub n times y sub n. So I'm going to put these formulas in a box. I'm also going to go back here and also put this formula in a box. So now, keep in mind of what we're actually looking at here. In order to find a moment about x, we actually take the mass and we multiply the mass times the y coordinate. Okay, the reason why we multiply the mass by the y coordinate is because when we look at the mass of a system, the moment about x has or uses y as its sides. Okay. So I want you to keep in mind we're finding a moment about x, but we're multiplying the mass times the y coordinate. Right. So if I look back at what we were given, I'm going to take m sub 1, which is 7, and these points, this is my ordered pair point x comma y, right? In any ordered pair, you must have x and y. Since this is my first point, I'm going to call this x sub 1 comma y sub 1. Since this is my second point, this is x sub 2 comma y sub 2. And for my third point, this is x sub 3 comma y sub 3. So to find the moment about x, I'm going to take m sub 1, which is 7, times y sub 1, which is 4, plus m sub 2 times y sub 2. So m sub 2 is 8, y sub 2 is 1, plus m sub 3 times y sub 3. So that's 3 times negative 4. And if we multiply all those things together, we have 28 plus 8 plus a negative 12, which is 24. The next thing we'll do is find the moment about y. So that formula is m sub y is equal to m sub 1 times x sub 1 plus m sub 2 times x sub 2 plus m sub n times y sub n. that's x sub n. All right, so in order to find the moment about y, we're taking the mass times the x coordinate. Right, so for my first term, I'm going to take 7 times -1 plus 8 times -9 plus 3 times 8 So the moment about y is, so that's -7 minus 72 plus 24 is -55. All right, so we know the values for m. We know the values for the moment about y and the moment about x. Okay, so now here's where you have to be careful. Once again, notice in order to find the x coordinate, it's the moment about y divided by m. I'm going to put another step in. So the fourth thing we do is substitute into the formula. So I'll just write that formula once again. X bar, y bar is equal to the moment about y divided by m, comma, the moment about x divided by m. Okay, so I'll just substitute in those values. The moment for y was -55 divided by the mass of the system, which is 18. To find y bar, we take the moment about x, which is 18. Excuse me, we take the moment about x, which is 24. We divide by the mass of the system, which is 18. And that should give us our system. That should give us the coordinates for the mass of our system, which are -55 over 18 and 4/3. All right, so that would be the coordinates for the mass of our system. All right, so just to go back, and just kind of review what we did. Okay, we were finding the mass about our system. All right, so we had the mass for object 1, the mass for object 2, the mass for object 3. We were given the locations for those masses. Remember, this can be mapped out on a coordinate system. We then wrote out the formula, right? We found the mass of the system by adding up each individual mass next. We found the moment about X, right? So be careful when you find this moment about X. It requires you to multiply the mass of your object times the Y coordinate, right? So we multiply each mass times its Y coordinate. We sum those to find the moment about X. To find the moment about Y, we multiply the mass for each object times the X coordinate, right? We got negative 55. We substituted in everything and we got negative 55 over 18, comma 4/3. Here again, you must be careful. All right, so X bar, that's equal to the moment about Y divided by M, and Y bar is equal to the moment about X divided by M. So keep in mind that the moments are just the measure of the tendency to rotate about an axis. Okay, so just keep in mind that there's a reverse on the axis, so to speak. All right, we substituted those into the formula and we had negative 55 over 18 and 4/3. All right, so if I put that in, negative 55 over 18 and 4/3. Oh, you guys can't see this. Let me click back over. All right, so we have the coordinates for the center of mass. All right, now here's where problems 2 through 6 differ. There is a different set of formulas. Okay. So keep in mind, using these formula, you can only use this formula if you're given the mass of each object and you're given a location. Okay, so I'll go back. You guys can't see that. All right, so in order to use this formulation, you must have the masses, and you must have a location for the masses. All right. Okay, for problems 2, for the rest of the problems, all right, 2 through 6, notice I'm not giving any masses. Okay, and I'm not giving any, well, I'm giving some coordinates, but I'm not giving a mass. All right, so notice here I'm not giving any masses. I'm just sort of giving a couple of equations. All right, same thing for the rest of the problems. Here is the formula, or here are the formulas that we will use. Okay, I'll just write them down. Okay, this is just sort of to set things up for the next class. All right, because we won't have time to work out. These problems are really long, but this would be the center of mass and it's still X bar, Y bar. And the X bar, okay, let me make these look like X's and Y's. Right, X bar, that's equal to the moment about Y divided by M. Y bar is equal to the moment about X divided by M. All right, so M was still the mass of the system. M is still the moment about Y. M of Y is still the moment about Y, and M of X is still the moment about X. Okay, here is where things change. M, right, which is the center of mass. Before we could just add up our masses, but in these instances, M, that's equal to K times the integral from A to B for f of x minus g of x dx. Right, so you'll notice here that there is a different formulation for M. The moment about X, right? So notice that this K is attached to this function, all right, or to this integral. So you'll be given an f of x, you'll be given a g of x. You may or may not have to find the limits of integration, but you must attach K. Right. So the moment about X, that's equal to K divided by 2 times the integral from A to B for f of x squared minus g of x squared dx. So notice that this is entirely different from the previous example where we sort of multiplied the mass times the y coordinate. Okay, here there is an integral to find the moment about x. Now, in order to find the moment about y, we're given k times the integral from a to b for x times the quantity f of x minus g of x dx. All right. So notice in order to find the moment about the y-axis, there is an integral versus simply multiplying the mass times the x coordinate. Okay. All right, and this is to find the center of mass of a region. Okay, so it all depends upon what you're given. Okay, if you're given the masses and if you're given the coordinates for each mass, there's a set of formulas to find the center of mass for that region. However, if you're given anything else, okay, this is what you must use. Okay. So we actually take a look at an example on this in the next class. Okay, because there's 3 integrals that we have to work with. We'll kind of make the math a little bit easier by using the calculator. Okay, but before we even get into any of that, I want you to understand that these are where there's differences, okay, in the center of mass, depending upon what you're given. There's also differences in the formula itself. All right, so with that being said, I'm going to stop the recording.